Thank you very much for the kind introduction. I'm very honored to give this Charney lecture. Yes, I'm very delighted to do so. My voice will come down. But it's my great pleasure now to take the next 50 minutes to talk about what my passion is, clouds. And I do that in all aspects, in all different facets, from ice nucleation in the lab to field measurements at the Jungfraujoch, from where you see a picture being taken in clean air when you can't be in the clouds, and all the way to climate. Those of you who know me know that I started out as a climate modeler, but by now I do all different things. And I've chosen a title that's wide enough that I can capture all the different things in there. But to motivate this a little more generally, why would we care about clouds? I think you can just enjoy them when looking at them. But of course, there's also dangers to that, like aircraft icing that we want to prevent when an aircraft flies into a cloud that's at sub-zero temperatures and would ice over, with big hazards that can happen. Or, especially here in the States, we know we have big hazards from tornadoes, or cloud dynamically on a much larger scale, what also Peter Webster worked on, tropical cyclones. Cloud in all their facets, cloud dynamics, cloud microphysics, pick your choice. Or you could be just curious to look at the beauty that's out there and the curious looking ones which look like that as if somebody punched a hole through them. And this somebody is an airplane creating so cold temperatures that, can you go back please? This is the pointer, here, getting there. That the cooling that the aircraft induced led to this cloud surrounding it is all composed of water droplets at temperatures below zero. But because of the huge cooling that was introduced due to the aircraft, the cloud droplets froze, and the ice crystals grow rapidly at the expense of the water droplets, and you see them falling out of the cloud. If we were to understand clouds, there have been discussions coming about, could we modify them either, say, for weather modification or on this aspect to engineer climate? So there's many different aspects of why we could be interested in clouds, and what I will tell you about is how they matter for the radiative forcing. So what happened due to human activity? Radiative forcing means that you have an external perturbation to the system. Doing that, we realized that there's lots of uncertainties with clouds, and the ones that I'll focus on more than are the ice crystals, because we understand them much less than the liquid ones. And then I will also turn it the other way around and look into the future. How important are clouds for climate change? And could we geoengineer or climate engineer them in a way? And then I'd sum up. So, what has happened? I think most of you know that, oh, this is the old version of the talk, doesn't matter. As I said, radiative forcing imposes an external perturbation to the system. What has changed? We have emitted increased carbon dioxide emissions. Carbon dioxide is a well-mixed greenhouse gas. You don't need to show it on a geographic distribution. If we look at aerosol particles instead, what you see is there's a large variety of them. You see, for instance, dust here in this yellow-orange colors, mainly emitted from the Sahara and the deserts. You have it here over the Himalaya. You have it there over Australia. You see sea salt whenever we have rough oceans, mainly here in the Southern Ocean. You see it also here. You have organic aerosol particles shown in green, both from wildfires, biomass burning, also trees in the summertime. And last but not least, we also have sulfate aerosols. They do have some natural sources, but what you see here is where they come from industrial activities. You see them here over Southeast Asia. And you see that those aerosol species are very inhomogeneous. You see that they can be mixed, there can be different species at once, and the huge spatial structure that you see is because they have a very short lifetime, on the order of a few days to weeks, and then they are removed from the atmosphere. So they are harder to understand because they are spatially so variable. What do those aerosol particles do? For one, they scatter solar radiation, or some of them do, and that leads to a cooling. With time, there are just some adjustments taking place, and then the cooling will spread out and cover a much larger range. But you also, like black carbon or soot, is absorbing solar radiation, and that leads locally to a cooling, but the solar radiation that's absorbed doesn't make it all the way to the surface. So below there, initially, you also have some cooling. If you wait some time, this turns into a warming. The other aspect to it is that the aerosol particles influence cloud formation. In fact, we wouldn't have any clouds if we didn't have any aerosol particles. Then we wouldn't need relative humidities of several 100% to form a cloud just from the water vapor. That doesn't happen, as you all know. Relative humidity does not get that high, and that's because we have the aerosol particles there. So now if you were to compare a clean cloud, as shown here on the left, you see that it forms some cloud droplets. The cloud during the daylight reflects shortwave radiation. If it's over the ocean, it may rain. If we now pollute that, and if we add more cloud droplets, more aerosol particles, we form a cloud that consists of more but smaller cloud droplets. So that increases the overall surface of the cloud and reflects more radiation back to space. It may also, that's something we don't know, if you have more and smaller droplets, it's harder for them to collide with each other and form precipitation-sized particles. So that may also have some implication on their precipitation formation, but that's much more uncertain. Do we have evidence that aerosol particles really form clouds? Well, you wouldn't need to go somewhere where it is so clean that you don't have any aerosol particles. And we actually did that. We went to the Arctic in 2008 in summer to approximately 87 degrees north with outside temperatures of -8 degrees. There the aerosol concentration less than 10 per cubic centimeter, which is less than, now I see if this works. No. Could you go back and start the movie for me, please? Okay. So the demonstration here is at -8. If you took outside a cup of tea, you should see this steam coming out of it. You see a little bit of steam, but not what you would normally see if you are here in a bigger city, like, for instance, San Francisco. Now, to demonstrate that, you need to find a source of aerosols to really tell you that this is what is missing there. By going in, what they see, they run into somebody. With a lighter. Now you see, the minute you have a lighter, you have a source of aerosol particles, you see them. So it's very simple. Without aerosol particles, no fog. Okay, so having said that, we can now put that together. The radiative forcing that has happened since pre-industrial times is best summarized in the IPCC bar chart. We know the positive forcing from the well-mixed greenhouse gases, starting with carbon dioxide. We understand that very well, high confidence level. The other well-mixed greenhouse gases also add to a positive forcing. Here is just the aerosol radiation interactions where aerosols scatter or absorb radiation. And below, this is our aerosol-cloud interactions, that aerosols make the clouds brighter. What you see is that's the only thing on this bar chart where the confidence level is low and the uncertainty is largest. Now, I have already shown you that this is because, for one, aerosols are spatially very inhomogeneous. The other thing is also that clouds have small-scale structures. So where would you go to see that? We have observations from that if we look at satellite data over the oceans. And now, in contrast to the contrails that you used to see when you look upward, here you are in the boundary layer, in the marine boundary layer. And we know that in the marine boundary layer, it's moist enough so that water vapor is not contributing to the ship tracks, but it's those particles. There's quite an old experiment off the coast of California that flew with airplanes through such a ship track, and the ship track is between those two lines here. You see the background cloud here with aerosol concentrations of around 100 per cubic centimeter, and within the track it's a factor of 10 higher. That also is shown here, seen in the cloud drop number, factor of 5 higher cloud droplets or 3 higher cloud droplets. They are smaller and they reflect more radiation. So you see that visibly. We have done a case study to see if we can simulate that. And this is over the Gulf of Biscay with Spain and France here. And let's just focus on those ship tracks that you see there. The model simulation is a 2 by 2 kilometer regional model. If we just have no ship emissions, you see that this background cloud here is well captured in terms of its optical depth. But of course, there is no ship tracks, right? If you add the pollution into that, then you see we do capture those. Now you could say that's trivial, but ship tracks don't form that often. They may be visible less than 10% of the time. So you need certain conditions of the boundary layer for that. But we have warm clouds, and these are water clouds, rather well understood. Now let's turn to ice, because what's missing in this estimate here is that aerosol particles also influence the ice clouds, the high cirrus clouds that we have in the upper troposphere. There has been one study a few years ago where we tried to quantify that effect. Let me start by showing you the aerosol forcing here now. And you see that it's negative, so we reflect shortwave radiation back to space, locally up to 12, 15 watts per meter square. This is largest in that model over the Pacific, and it's larger over the northern hemisphere where we have all the pollution going on. This is only water clouds. If we then also let the aerosol particle influence ice clouds, and I will tell you much more about how that's done, you see that there's the negative forcing is reduced. What that means is there are clouds out there that have a positive forcing. That works in the same way as the greenhouse gases work. So they don't offset any of the greenhouse gas warming we have. And substantially, this could be large. The estimate from that paper is that it's approximately a third of what we in the IPCC had as the total aerosol forcing. What this also means is we ought to understand ice formation better, and that's what I will be turning to now. What is it, or why is ice formation so hard to understand? That is because the sheer number of aerosols acting as ice nuclei is much, much smaller than those acting as cloud droplets. We only have 1 in 100,000 or 1 in a million. So we have to literally look for the needle in the haystack. We do know a little bit about it because we know what the fundamental difference is. aerosols acting as centers for cloud droplet need to be liquid or hydrophilic, soluble or hydrophilic, because they need to take up water, whereas those that act as centers for ice crystals should be either solid or crystalline. If I show you the variety of aerosols that we have, what you see is that aerosol particles, they are here classified as a function of size. In number concentration, we have, for instance, sulfuric acid, which I showed you comes from anthropogenic activity, or also carbonaceous particles as being the smallest. And that they are all good cloud condensation nuclei, like sulfuric acid, ammonium sulfate, organics, sea salt, biomass smoke. We have quite a lot of them. Ice nuclei need to be those that are solid or crystalline, and the ones that we have are mineral dust, biological particles like bacteria, pollen, or fungal spores, or maybe in crystalline form ammonium sulfate. So there's differences in sheer number. Also, if you want to go out and measure them, if you want to measure cloud droplets or those aerosols acting as cloud droplets, you can go, if you have the money, buy the instrument, go out in the field, you are done. With ice crystals, you first need to build an apparatus that does that for you. And because of that, there exist quite a few different ones in the field, but the technology is much newer and much more prone to some errors that we don't understand. And last but not least, there are several ways in which ice can form, whereas for cloud droplets to form is very simple. You have your aerosol particle, water vapor condenses onto that, it grows, done with. For ice crystal formation, you first have to, you can have homogeneous freezing at temperatures below -38, but you could also have an aerosol particle on which water vapor deposits, or it could be immersed within the cloud droplet and initiates freezing from within, or that same can happen upon contact. So many different possibilities that you have there. We also need to distinguish two different types of clouds that contain ice. Ones are clouds that form at temperature warmer than -38, where potentially both ice crystals and cloud droplet can coexist, and below -38, the cirrus or pure ice clouds. You will see some of those diagrams again. Here is the temperature on the x-axis, ice saturation here, but because we have a difference in vapor pressure over liquid and water, that if you are at water saturation, you are supersaturated with respect to ice, and this supersaturation increases by approximately 10 to 12 degrees per 10 degrees supercooling. So what that means is once you have ice crystals being formed, they are an environment where there's a large supersaturation with respect to ice, and they can go rapidly at the expense of droplets. Now, the pathway that we look at in the lab, which turned out to be the most important for mixed phase clouds, is emergent freezing, where the ice nucleus is already immersed into the drop. Okay, how does that happen? We turn cloud formation upside down. We start with producing the cloud droplet on the top, and then it goes down into the ice chamber, and so we just put the atmosphere in a reversed order. Schematically, what it is that we have what we call a continuous flow diffusion chamber. So you have the air come in, and that is between two walls that are at different temperatures. How that works is that here's your cold wall, here's your warm wall. You establish a linear temperature gradient and a linear gradient in water vapor. But because the saturation vapor pressure depends exponentially on temperature, you are supersaturated with respect to ice, and depending how high or how very different the temperatures are, you can be also supersaturated with respect to water. And now in the middle of that, the aerosol enters, And so then the aerosol is exposed to this supersaturated air. And that happens here. This part here is basically our main ice chamber. At the bottom of it, we put both walls at ice saturation so that the cloud droplets can evaporate, but the ice crystals don't. And then we can see and count our particles. If we do that, or everybody in the field, here is what we as a community know. Again, the same type of diagram. You have saturation ratio with respect to ice here, temperature here. Let's focus on those mixed phase clouds first. You see that those bioparticles, pollen, bacteria, leaf litter, fungal spores, they initiate freezing at the warmest temperatures. So generally speaking, the more you see points down here, the better those aerosol particles are for ice formation. And there seems to be a rather narrow line where those bioparticles can be. If you look at mineral dust, where we as a community agree upon that it's the most important ice nucleus, you see data all over the place. This tells you that we don't know anything about it, but it relates to some of the measurements difficulties that we have. Every chamber measures something that's slightly different. If you want to take one message away from here, is that there are for dust 2 different symbols, with the stars down here showing that the particles are larger than 1 micrometer. And the larger the aerosol particles are, the better ice nuclei there are. So the stars are predominantly down here. But why is there such a large variety in mineral dust? That's something that people have been starting to look more into it. There has been a paper out of that by Atkinson et al. Last year in Nature. What we mainly studied in the lab is clay minerals. Clay minerals, for instance, like montmorillonite. What's shown now is the frozen fraction as a function of temperature. Down here, you are at homogeneous freezing. What we are looking for are particles that initiate freezing back here. The clay minerals that have been predominantly studied are not so efficient. But recently it was found that there is the feldspar component, and especially if it's potassium feldspar, then we see ice formation at rather warm temperatures occurring. And that's something where we also thought of looking at this in the laboratory. And if you do that, and then you start to talk to geologists, they tell you, well, what feldspar do you really want? There is not just one potassium feldspar. And so our geology department gave us 5 different ones, 4 of which you see down here. And just by looking at them, you realize that they have different colors, so they probably also have differences in morphology. And the way geologists like to do that is that they classify the amount of potassium on there, or sodium, or calcium in this triangle, and there's only very distinct parts of this triangle where you can be. So let's just focus on those 5, which all belong to this potassium feldspar category. We measured them in the lab. So here's the frozen fraction again as a function of temperature. In gray is the homogeneous freezing. And now you see that all those 5 feldspars are also not the same. We see again the size effect. You see the size effect such that the larger they are, the warmer the temperature where they initiate ice. But the size dependence also varies for the different feldspars. For instance, this auto class has only the 800 nanometer particles that are efficient, and the others don't do anything. Whereas the microcline Amazonite, you can activate 15 nanometer particles. So there's a large variety out there. Now, how does that compare to some of the particles that we understand? So back here, if we look at temperature, and the median freezing temperature as a function of size. So you see the size effect clearly here for clay mineral kaolinites. The larger the particle, the warmer the onset or the medium freezing temperature. If you add other clay minerals, they almost fall on top of each other, except for this ATT, for Arizona, Arizona test dust that is also, that when you analyze that in the lab, you actually see that it has a higher feldspar component on there. So the feldspar story seemed to hold. And now on top, you see this Atkinson et al., their feldspar results, and our microcline data nicely fall on top of each other. But the other feldspars that we looked at, they are at the much colder temperature. And the Sunny-Dean, for instance, that I think is a Swiss feldspar that doesn't like to freeze. We can also compare that to the biological particle that I didn't tell you too much about. They are large, they are hard for us in our chambers to measure, but people have been successful in just looking at the washing water, because if what is freezing from those biological particles is the protein, you will wash it off, you have it in the washing water, and you see it here. And yes, birch water is as good an ice nucleus, or the proteins from the birch, than the feldspar you have. But if you want to do the same with pine, for instance, it doesn't do you anything. So it's not that any biological particle is the same. The other question is, through anthropogenic activity, we have a lot of soot. What is that doing? I didn't mention it, and for mixed phase clouds, we also don't really need to worry about it too much, because it also doesn't do much. The question still is, are there particles around that are much more efficient? The one that we know, and that goes back to early days from cloud seeding to prevent hail damage, is silver iodide. But silver iodide is not atmospherically relevant. So we still have a question mark there, is what is really a good ice nucleus? With that now, I'd like to turn to some of our field measurements, because ultimately what we want to use our lab data for is to understand our field data. Now, if we go in the field, things become more complicated because we have many different processes occurring. So where we go in the field most often is on top of Jungfraujoch. That's a 3,500 meter high mountain in the Swiss Alps. That's approximately 30 to 40% of the time in the clouds and represents an ideal laboratory to measure clouds. What we have is a holographic device, so we can take pictures of cloud droplets and ice crystals there, and we also have auxiliary data like wind, temperature, and we also have our ice nucleation counter there. Now, I just said if we go out in the field, things become more complicated. And why is that? That is because in the lab, what I showed you is we isolated the first step of just here, this first ice formation. That we can isolate in the lab. In the field, you cannot. If we measure crystals in the field, we don't know if there has been a cloud above where the ice crystals fall through, or blowing snow from the surface that we may got into there, and that caused the ice to multiply. The other thing is, once we have our ice, the ice crystals start to collide with each other, become larger. Maybe some of them splinter, and we produce back many more smaller crystals. It's a whole zoo of processes that goes on. And that is my connection back to Brian Hoskin's talk here. In the field, we have to worry about dynamics. Now, ours are much more localized, but on the mountaintop, we have updrafts, downdrafts, turbulences, all sorts of things we also need to worry about. So, we have done our first measurements, and let me put them into context. Ice microphysics has been pioneering. Here in the States, you have long tradition of measurements. Canada, Alexei Kovalev mixed phase clouds, aircraft measurements. And what's shown here is the ratio of ice to total water. Total water is the sum of liquid and ice. And you see that predominantly we have either water or ice. But we don't seem to see coexistence of ice crystals and cloud droplets occurring too often. We look at our Jungfraujoch data. We find the same if the wind comes from the south. But a different story, much different picture if the wind comes from the north. All in a sudden, we are able to have a coexistence of water and ice. And that can have two reasons. One is dynamical, one is microphysical. If we look at the topography of Jungfraujoch, you would say very likely this is dynamics, because the south slope is much smoother than the north slope. We have much steeper terrain, so we expect much higher vertical velocities. It's likely true. We unfortunately don't have vertical velocity measurements, so at that point we are guessing. We are also trying to relate that back to our ice nuclei measurements. But when you look at this, now this is ice crystal concentration versus temperature. These are our concentrations from the holographic device, stratified to north and south wind cases. You see that the colder it is, the more ice crystals you have. But if you were to extrapolate that, we have 3 orders more ice crystals than ice nuclei. That's a known problem in cloud physics. It's called ice multiplication, secondary ice formation, that the crystal concentrations exceed the ice nucleus concentrations by orders of magnitude. And if we were to extrapolate that further, it would be the same everywhere. So it's definitely not that our ice nucleus measurements help us here to understand that at this point. With that, I want to switch to now looking at the cold clouds, the cirrus clouds. What is happening here? We can have cirrus clouds forming by homogeneous freezing, but it would be freezing of solution droplets. This is not on the water saturation line, because as you in winter put salt on the roads to have a freezing point depression, also a solution droplet that has salt in there freezes at colder temperatures than pure water, and you see that here. But we have enough sulfuric acid particles that would homogeneously freeze the solution as solution droplets. Or we could again have some aerosol particles acting as ice nuclei and causing those cirrus clouds to start ice formation at much smaller supersaturations. What is happening? We did some lab studies on that a while ago, comparing, same diagram, saturation ratio with respect to ice as a function of temperature for sulfuric acid and ammonium sulfate. Let's start with the sulfuric acid. You find that most of the data from many different institutions, different measurement devices, all show homogeneous freezing, which makes sense because sulfuric acid is liquid throughout, that never crystallizes. And that occurs, that also matches field observation in the southern hemisphere. If you go to field observations in the northern hemisphere and old data from Heimsfield and Milosevic, you see that cirrus were forming at different conditions. And now if you look at ammonium sulfate, the different measurement devices that are out there have a much higher variety of where they say that ice crystal formation occurs. And that is because in some devices this ammonium sulfate is crystalline, and in others it's not. And now you capture the range of observations in the northern hemisphere that have lately also been shown by Dan Sitzo last year to the southern hemisphere. And it's not, we are not the only one finding that, because if I now show you the second part of this diagram, you see that ammonium sulfate could really cause ice formation at smallest supersaturations, similarly well than mineral dust. So we have, again here, mineral dust playing a dominant role. We can combine now our experience with the lab with modeling results and look at the global impact of that. What I'm showing you here is a cross-section from the South Pole to the North Pole, vertically integrated ice crystal number concentration. If you have homogeneous nucleation, you see that you have most particles in the northern hemisphere. That's where we have our maximum von sulfate particles. We have additionally peak in the tropics, where we have lots of cirrus clouds as well, and then in the southern hemisphere. If all of those particles, the ammonium sulfate, were crystalline, what you see is that the ice crystal concentration would be much smaller. And if just a fraction of that were to freeze heterogeneously, it would be in the middle. If we did the same with mineral dust, then we reduce the ice crystal concentration even more, because we have less mineral dust around than we have sulfate around. What would be the radiative impacts of that? Cirrus clouds do actually both. They trap long-wave radiation, but reflect also short-wave radiation. Now, this is all compared to homogeneous freezing. So if we make the cirrus cloud now having fewer, larger crystals, we do an inverse ship track. And so this inverse ship track is shown here by reflecting less short-wave radiation back to space. On the other hand, more long-wave radiation can be emitted to space, and the long-wave effect is approximately twice as large as the short-wave effect. And that can be a negative forcing of up to 2.5 watts per meter square. This is larger than all the anthropogenic forcing we had since pre-industrial to today, so that would be a large impact. We are doing that now a little bit more sophisticated. We can also take the competition into account. If you looked at a parcel model, what would happen? If you start here, this is time, you start to have an air parcel lifted, expand, cooled, and the supersaturation increases until homogeneous freezing sets in, and then you quickly reduce the supersaturation. In our example, say you created 700 ice crystals per liter. If you just had a few ice nuclei, 1 and 1 per liter, 2 different kinds, you start to form ice first, but the ice crystal concentration is so small, the supersaturation still rises, and you end up with a similar number of crystals. But if you had 100 ice nuclei, and we have here mineral dust particles, then the cirrus cloud would form pure heterogeneously and only has, say, 7 times less ice crystals than up here. So there is the possibility, if we have a heterogeneously formed cirrus clouds, it is optically less thick. So we do this inverse ship track. If you show it here now, it's the differences between pure homogeneous freezing and taking this competition into account are not that large anymore, because it's limited pretty much to where we have mineral dust here. And what you do see, though, that it's important that we consider also the ice that has been there previously. That normally is forgotten if you always only activate new particles. So you find some differences in the tropic, but the differences are not as large as we had them previously. What implication does that have for climate change? And that's the second last topic that I'm coming to. We know it's getting warmer. This is the industrial record. How much warmer it gets in future remains open. That depends on what we are doing. How do clouds come into play here? Clouds do 2 things. If you look at the energy budget, water clouds mainly reflect short-wave radiation. Of the 340 watts per meter square coming in, they do reflect 50 watts per meter square. So those low clouds cool. The cirrus clouds that I just talked about do the opposite. They act like greenhouse gases. They basically trap part of the terrestrial radiation emitted back to space. That effect is approximately 30 watts in the current climate. So at the moment, current climate, the cooling effect of cloud dominates. But when it comes to climate change, we have two possibilities. If we get more of those water clouds, we will reflect more radiation back to space, and this will cool. If we have less of them, that would warm. If we have more cirrus clouds, on the other hand, that would be a warming. Fewer cirrus clouds would be a cooling. Four possibilities what can happen. Now, we need to turn to the models to tell us what is likely to happen. This is an old graph by now, but a nice illustration. This is the change in temperature for a doubling of CO2 from different climate models, and two are picked out here. It doesn't matter which one they are, just for illustration. One climate model where the warming has been rather modest, and shown here is the change in low cloud cover, with positive colors indicating it's increasing. So we have more of those cooling agents over the ocean, where otherwise we have a very dark surface and the warming is moderate. On the other hand, if you reduce those low-level clouds, we end up with a much higher warming. And even the last IPCC report said that the spread in how low-level cloud change with climate is one of the largest uncertainties out there. What do we know about ice? There has been a brand new study out there where they actually combined satellite CALIOP data with ECMWF reanalysis to look at the change in cirrus clouds. And what you see that this is the change in cirrus cloud cover, that it's getting warmer, high clouds, the troposphere expands, high clouds rise to higher altitudes, and then they trap more radiation, so the warming effect of cirrus clouds will be increased. They estimated that to be a 0.2, with this large uncertainty, the same uncertainty, plus minus 0.2 watts per meter square per degree centigrade, which would be a third of the overall cloud feedback that we have. We try to say what we know about clouds in the IPCC report, what of the responses that we have are robust. We see this rising high clouds that I just shown you in red indicates that it's a robust response. So a positive cloud feedback here. Also, a poleward shift of the storms. And what that does is that it shifts those low-level clouds into higher latitudes where there's less sunlight, so they can reflect less sunlight in a warmer climate. So the cooling effect of those is decreased. But that is indicated in gray, and gray means we know the physical mechanism, but it hasn't been collaborated. Okay, now that I've shown you that cirrus clouds enhance the warming, I should also tell you that people have been starting to have the idea, is there a way that we could make them less thick? And that is called geoengineering or climate engineering. And so we are just reversing that. So this would be an unseeded cirrus cloud, would be composed of many small ice crystals, and that would be a seeded one or a heterogeneously formed one. And so you see it reflects less shortwave radiation, but also more longwave radiation escapes to space. That work has been done by Trude Storelfmo and colleagues, and it's shown here. They explored that what would be the optimal number of ice nuclei that you would need to seed the cirrus cloud with to achieve the optimal cooling effect. So this is the change in the cooling you would get versus how many ice nuclei do you need. And what you see is that the optimum is here. You reach a negative forcing of about 2 watts per meter square, but only if the background cirrus clouds are homogeneously formed or a competition between homogeneous and heterogeneous. If all of them were formed heterogeneously and you add more ice nuclei into that, then what you do is the same as with water clouds, or what I've shown you as the ship track. The clouds just reflect more and more shortwave radiation. And then you would add up with exactly the opposite effect. Okay, and with that, I've come to the end of my talk. What did I show you? I showed you that by now we have realistic simulations of ship tracks. that can help us constrain the aerosol radiative forcing. We have also identified which atmospherically relevant atmospheric ice nuclei are out there and how they compare to each other. And that if we compare heterogeneously formed cirrus clouds with homogeneously versus homogeneously formed cirrus clouds, there would be a negative radiative forcing of approximately 2 watts per meter square. The question is, what is the outside world doing? So the open questions that we have, and this is just a few of them. How important are the ship tracks that we have seen globally? We knew that we used them as nice test beds for aerosol cloud interactions, but do those matter? We don't know. The ice nuclei that nucleize ice first at the warmest temperatures, we don't know what they are. The bioparticles, according to our model studies, don't exist in large enough concentrations to make it to those altitudes where the clouds are. So if they are not there, then how important are other ice formation mechanisms? And the big question, are cirrus clouds predominantly formed homogeneously or heterogeneously? There's been a study by Dan Sitzo last year arguing that most of them actually are formed heterogeneously, especially when you are in areas where you have lots of mineral dust. So if you're curious now about ice processes, I should advertise that there's an ice session starting at 4 p.m. this afternoon over in the Moscaine West building. And before I thank you, I would like to thank all my research group whose results I have presented here, and I'd like to thank you very much for your attention.
Thank you for a marvelous talk. We have some time for questions. Somewhere out there in the glare of the light.
It's not so bad. I think somebody's coming on.
Okay. Yeah. Yeah. Mm-hmm.
So in the figure from the IPCC report, you showed that you projected that the storm tracks would change in latitude. With those changes in latitude with the storm track, do you expect maybe the areas of desert to expand and potentially changes in ice nuclei concentrations? Like, people are looking at a lot about how sources of moisture and things are going to change in a future climate with rising temperature, but how are ice nuclei concentrations going to change? Are people looking at that? And how much you then relate that to the formation of ice clouds?
Well, actually, the simulation of mineral dust in our models has proven to be not the easiest. We have been looking at the contributions from land use changes, which would be that, or desert expansion versus anthropogenic. And at the moment, I've forgotten what the answer is, how important that is.
Yeah, thank you.
I do have one question. The very first diagram you showed was the NASA diagram, which separated black carbon and mineral aerosols and so on. But then you made the point that all mineral aerosols aren't the same, especially the feldspar. So could you refine that diagram for specific geographic locations where you might find certain types of feldspars which would freeze at lower temperatures?
Yes, I mean, Jim Atkinson and I, they tried to simulate it, and they realized that they were limited, the areas where the desert goes to. So they also need to invoke some other ice nuclei elsewhere. We have some information about mineralogy. That's basically at the surface where the sources are. In order to transport them all around in the models, it would require quite some computational overhead. It's probably one of the next things to be done to take the different components, but I'm not sure if you have this composition everywhere. And I think we are just trying as a community, we're at the point to understanding how important that feldspar is. For instance, there's some aging effect also, that the feldspar is turned into a clay mineral that way around, yeah? That the feldspar goes into a clay mineral as it ages, and then the question is how much of that you really save. And that would be all very complicated to consider.
I guess I can make one small comment. It makes potential vorticity seem very simple.
That is not an nemesis saying
Okay.
that.
So here's a question here. So you talked about the, from a climate change point of view, the different role played by the low clouds and the cirrus and high clouds. But observation shows that, especially in the tropic, there is a kind of almost like a trimodal distribution of congested clouds. In fact, Dick Johnson's work shows that there's a high abundance of it. And in fact, looking at the IPCC and also the CMIR5 model, I think there is a general, very robust response in terms of reduction in mid-level relative humidity. And so there is going to be a large change in the middle clouds. So I'm just wondering, from the climate feedback perspective, what would that do in terms of getting the balance between the low and cloud? The middle clouds do play a very important role in terms of dynamics and maybe also cloud forcing. I'd like to hear your view on that.
You're the expert on that, right? So that's not fair. No, to my understanding, the mid-level cloud, it will easily set there somewhere in between cooling and warming, right? So they probably don't do too much, but then it would also depend on how they. Then if the dynamics come into play, if you remove something that's dynamically important and you tend to move the cloud systems around and put them in different places, that can lead to all sorts of feedbacks. I think in terms of climate feedbacks, I was actually in the feedback session yesterday, and the answer I got there when I was asking why some person did not show cloud feedback, because they say it's way too complicated. We are not there at that point that we can quantify that, unfortunately.
Just before we say thank you to Ulrich, putting on something like this in these rooms takes a lot of work, and I'd like to thank our section secretaries, Thanos Nennis and Melody Avery, for being somehow able to arrange this marvelous venue for these talks. And Ulrich, thank you very much.